Okay, in this session, we're going to look at using Nix fuzz. And we're going to take a look at first, what exactly is Nix? Why do we care? How it's architected in general, and how we can leverage this for full system snapshot fuzzing with device emulation. So we've looked at other fuzzers like What the Fuzz and userland-based fuzzers like WinAFL. And similarly, there's AFL++ and Hong Fuzz and much more. But what Nix is firstly the hypervisor and emu based fuzzer. It combines both in the sense that device emulation is handled by QEMU and actual execution of the CPU, so I guess CPU execution, is handled by KVM. The way this works is that uh, as I guess just a general overview of this, you have QEMU. QEMU is an emulator. It has various components. One of those components is virtual devices, which I'm going to call VDEVs, or virtual devices, right? VDEVs are emulation components of devices, things like um, hard disk drives, things like your NIC, and your network card, and another device, maybe something like stereo, and there's much more, right? This kind of replicates, in QEMU you got a dash device command line option where you can specify multiple devices. These are all just virtual devices, the emulated devices. That's part of QEMU. And then there's also the CPU executor, right? For example, if it comes to like what actually executes MoveRack's RCX, right? This is a CPU execution, a CPU instruction, right? Component. Now, when it comes to actually, so we know that the VDEVs handle emulation of the actual device hardware, but what about the actual CPU instructions themselves? There's a couple components for that. There's either what's called TCG, um, tiny code generator, I think it is, and this is pure emulation. This is where in QEMU it has its own code for decoding an instruction at an address in memory and emulating it. So that's a pure emulation way. But QEMU does also have um, hypervisors. It can leverage hypervisors to execute the actual CPU components. On Mac, it can leverage Mac OS's hypervisor.framework. Let me adjust this. Yep, so on Mac, it can leverage hypervisor.framework on Mac OS. On Linux, it can leverage the KVM hypervisor present on Linux. On Windows, it can leverage I believe it's the Haxon kernel driver that it can leverage for hypervisor-based execution of the CPU on Windows. And there may be more, I'm not too sure, but I know there's at least these ones. So what's the difference, right? When it comes to CPU component execution, obviously if it goes a TCG route, it's pure emulation. It doesn't need a hypervisor to be present at all. So if you're running on a system that does not have a hypervisor, you can run it on QEMU on that host. Additionally, if you're running it on a hypervisor, remember QEMU supports more than just x86, right? It can emulate ARM and other devices. But the hypervisor that it executes with has to be the same architecture as the target because that's running on your host. So with TCG, you can run, say, an ARM64 guest on a x86 host, but you wouldn't be able to leverage hypervisor in that scenario because your hypervisor would be your host architecture, which would be x86. It wouldn't be able to run your ARM64 guest. But in the case of where you're running the same architecture, so I'm running, move RX, RCX is, x86 instruction. I'm running an x86 guest, and I have x86 host on either Linux with KVM or Mac OS with hypervisor framework, or Windows. Then you can leverage a hypervisor. And what that means instead is that QEMU will work with the hypervisor such that the hypervisor will execute the raw CPU instructions. And whenever it needs to handle something like access to a device, like a NIC or a hard drive or serial, the hypervisor will call into QEMU. QEMU will call into its virtual devices, emulate it, and then jump back to the hypervisor that will emulate or continue emulating the raw CPU instructions. Now, because the hypervisor way, or in that method, the actual execution of these instructions are happening natively on your CPU, performance with the hypervisor is generally better than with just TCG. Because with TCG, you're not directly emulating this instruction. Instead, you're lifting this instruction to an intermediate language, perhaps jitting it, and then actually executing that IL in a way that makes sense in emulation. And additionally, because TCG is pure emulation, there's a chance for more bugs where QEMU may not emulate an instruction correctly. That's just a general difference between the TCG pure emulation route and the hypervisor route. So how does this kind of tie in with Nix? Well, Nix leverages both because it leverages QEMU, but it leverages QEMU with KVM, so in hypervisor mode. Nix also consists of KVM and QEMU patches for the purposes of snapshot fuzzing. By default, QEMU and KVM, they're not snapshot fuzzers. KVM can, take a snapshot of a VM and reset it, but it's not designed for performance in any way. And QEMU has emulation, like virtual device emulation, but it's not there in such a way that it's easy to serialize and snapshot at a point in time and reset for a guest. And there's other components there, like the actual input generation stuff and all that, but by default, QEMU and KVM, they're not designed for fuzzing. So as part of the Nix project is a custom kernel that consists of custom patches to QEMU and to KVM to enable snapshot fuzzing. So it has the emulated QEMU. Let me clean up this. So Nix will run on a custom Linux kernel. I'm going to call this Nix kernel. And this kernel will have a custom QEMU. Just delete that, I'll add it in. I'm going to call that Nix QEMU. And the benefit of having these patches is that Nix QEMU can fully snapshot and restore guests pretty fast. And the snapshotting encompasses everything. It encompasses, let me delete that, it encompasses CPU state, it encompasses memory, also device state. And by having all three, actually I'll leave that out. By having all three, it can quickly fuzz your target. Well, it can snapshot using the kernel and the QEMU. It can snapshot a guest at any point in time. So anything that runs on x86 QEMU, you can target. If you can get Mac OS on x86 running, or Linux on x86, or Windows on x86, anything you can run on x86 on QEMU should work. And I've tested this with Windows. You can run your Windows guest in QEMU up to any point in time you like, snapshot at that point in time, and then you have the entire dump of memory, CPU, and device state such that you can resume execution, which you can count as your fuzz case, do your fuzzing, and then reset back to the start. And we'll look at how this can be used in our harness. Um, so, and the way we get coverage, right? So QEMU does have or always keeps track of CPU state, right? It has to because it can snapshot it. It needs to know how to restore it, and it can always single step through the guest and query it. So while QEMU itself could be patched to do things and get coverage itself, the way that Nix is designed to get code coverage information out of your guest is through Intel PT or Intel Processor Trace. So if you want to do coverage guided fuzzing with Nix, you need to run it on a CPU that has Intel Processor Trace available to it. Most modern Intel CPUs do. If you're on an AMD CPU, you won't have this. That said, Nix will still fuzz and work on a CPU that doesn't support Intel Processor Trace. You just won't get coverage information. That said, if you're comfortable hacking on this code, you could always implement other ways in the Nix kernel to get coverage from the guest, or you could hack on QEMU and patch QEMU to extract out information relating to the executed instructions in the guest. But by default, Nix is designed to use Intel Processor Trace to track the CPU program counter of the guest as you fuzz. So we know about snapshot fuzzing. How can we leverage this for full system snapshot fuzzing with device state? I mean, that's the biggest difference between something like this and What the Fuzz. With What the Fuzz, and similarly designed snapshot fuzzers, you get CPU state and memory. So you can still fuzz, but the moment your snapshot tries to access a device like the hard disk, your fuzz case will fail because there is no device state. There is no saved and restored device state, only CPU and memory. But with Nix, you do get that saved device state such that if during your fuzz case, your target was accessing disk or another virtual device like serial, it would work fine. That would not be the end of your fuzz session because the device state is tracked, snapshotted, and restored at the end of fuzzing. And that's the biggest benefit to using Nix. And because Nix has a full CPU emulation, including nested virt, you can fuzz CPU extensions like the virtualization extensions, like Intel's, VTX and AMD's, was it like SVM? You'd be able to fuzz those. What this means is that you can fuzz Intel and AMD based hypervisors with Nix, because as part of its CPU emulation, it emulates even those nested virt instructions. So that also makes it a powerful tool for fuzzing hypervisors. Now let's take a look at an example harness to see how the snapshotting can work. So this here is a Windows harness that I have for KFL. This lives on my public GitHub. I go github.com/post22/kfl.targets. I forked the KFL targets from Intel Labs. Now under Windows x86-64, this fuzzer example is not currently updated to use Nix, the one included by Intel Labs. I imagine it will be updated at some point, but currently it will not work out of the box with Nix. They only have one target that works with Nix so far at this point in time, and that's this Zephyr x86-32 target. And it goes through of how to use it with Nix, but this is a 32-bit Linux target. On my fork, I updated the Windows x86 64 example in the fuzzer to work with NICs. If I take a look here, let's go to our main and walk through how this works. Now this is designed to fuzz a driver. The driver by default is going to be the included vuln driver. If I look at that source code, it has an iocto handler, and in the iocto handler, it checks the inputs of the user buffer. You know, that the first byte is a capital P, then a W, then an N, T, O, W, N, and if so, it crashes. So this is a good test for our fuzzer to see if it works. Because presumably, since it's a coverage-based fuzzer, if it hits this capital P as the first input, it should get new coverage thanks to the if statement. And then it should be able to build upon itself and form this input to cause a crash. So since this is a driver target, our harness is designed to interact with this driver. And it's going to be a good example on how you could fuzz arbitrary kernel drivers to begin with. But you could adapt the harness to fuzz anything. So this is our main, the entry point for our code. We have a payload buffer, which I just allocate some memory to. I'm allocating payload max size. These are just arbitrarily defined sizes. I have it here as 1028 times 1024. But you can adjust that as you like. We mem set it to 0, not only to initialize it, but just to make sure it's paged in. Now I open a handle to the driver. The driver installs itself with this symlink name, test KFL. So we open a handle to it, and then we init the agent handshake. This is going to initiate communications with NICs. If I look at this code, it calls custom hypercalls. These are the way we interact with NICs. Since NICs is a patch or includes patched KVM, KVM and QEMU have custom handlers for dealing with these custom hypercalls. If you look at KFL hypercall, all that instruction is here. It's a custom VM. It's just a VM call, right? On Intel, on Intel, a VM call is going to transfer execution from our guest to the hypervisor, and the hypervisor is going to query the registers of our guest and then do certain things based on that. And there's a custom hypercall handler that will handle our specific hypercall ID that we put in certain registers. And you can look for these hypercall handlers in the source code of the QEMU patches. So first, we do acquire and then release. This is the initial handshake with NICs. And then after we perform that, we submit our CR3. Why do we submit our CR3? Well, sometime during our fuzz case, NICs is going to have to inject input into the buffer that lives in our harness. Now, it's not enough for NICs to just know the virtual address of our buffer. Since that virtual address is going to mean different things depending on what page tables are loaded in the CR3 register, we have to tell NICs what our CR3 register is, so it can accurately send input into our input buffer when we eventually get to our fuzz state. We're not in our fuzz state yet. Next, we tell KFL we're running in 64-bit mode. And then we request information from KVM. We verify the magic and the version is as expected in our harness. Just some, I guess, stability-based checks. We have some informative prints. We make sure that the payload max size is at least as large as what the host is expecting it to be. And we configure our agent configuration with some basic defaults and submit that. So this is a pretty generic process that we can do in any of the harnesses we write. So continuing on, we go to init panic handlers. And we do this because NICs needs to know what addresses count as a crash. or Nix needs to know that when execution hits somewhere, it's a crash. Since we're fuzzing a kernel driver, any bugs that occur in a kernel driver are going to result in a blue screen. So we need Nix to know that whenever code goes to the kernel crash handlers, that means that we've hit a crash case. And here in init panic handlers, we have a dynamic ray to get key bug check and key bug check 2, which are the two main crash handler functions in the Windows NTOS kernel. We get their addresses and we submit both panic handlers to KFL. Now the way this is obtained is that we load the NTOS kernel from disk into our process space, and we get the offset of KE bug check and KE bug check 2. So if I were to visualize this, we have our process. Let me just grab. I'm going to name this harness.exe. This loads from disk C drive Windows System32 NTOS kernel.exe. Now, mind you, this is all in the source code as well. If I were to browse into this resolve key bug check function, you can see the source. I'm just going to visualize it here. Okay, if I think it's kernel.exe. Right, this is the Windows NT kernel. Now in here, there's going to be lots of functions. Two of them are going to be KE bug check and KE bug check 2. I think there's also KE bug check X. Yeah, but they're both the main crash handlers in the NT kernel. At least I think it's for this one. Let me see what I put in here. Kernel func 1 and kernel func 2. Kernel bug check and kernel bug check X is what I was using. So let's change this to kernel bug check X. So it's going to have those. Now when we load NTOS kernel into our process space, this is going to be loaded at some address. Let's say it's loaded at 0x13370000. Now let's say KE bug check X. Let me just take one of these. Let's separate them. KE bug check and another one called KE bug check X. We say KE bug check X lives at address 133.8.0.0.0.0, and let's say KE bug check lives at 0x1337.5.0.0.0. Right? Because this is the base address for NTOS kernel. The functions are going to live somewhere after that. Now I can't just tell Nix that the crash handler address is at 133.7.5,000. Due to like ASLR and things like that, the address that NTOS kernel is loaded into in my process space is arbitrary. It may be 1337 followed by zeros when it's loaded in my process space, but in the actual kernel, the actual NT kernel, this is the NTOS kernel that's running on our actual target, might be loaded at a completely different address, like FFFF 0x FFFF F8 1 2 3 4. It might actually be loaded at that address. And because of that, we can't just submit these addresses. That said, the offset is always going to be accurate. So this lives at 1337.5,000. If you grab that value and subtract the base address from it, we get the offset. So in this case, it would be 1337.5,000 take away 1337.1234, right? And what would we get there? We would get 0x5000. And the offset for KE bug check X from the base address would be 0x 1, 1, 2, 3, 4. Yeah, it would be 10,000. That would be the offset. So with these offsets, they're always static, right? KE bug check in this example is always going to be 0x5000 as an offset from the base address of NTOS kernel. So all we need to do is get the base address of the actual loaded NT kernel. In this example, if it was FFFFF 80,000, then that means that the address for, say, KE bug check would be 0x FFFFF 85,000. This address here would be this base address plus this 0x5000 offset would give us this address here, and this would be the actual address of KE bug check in the kernel. So by loading NT-kernel on disk, we can get the offsets of the crash handler. And with those offsets, all we need is the base address of NT-kernel. And we can get that by using the Windows APIs to query loaded drivers and devices and find the NTOS kernel entry and then extract the base address from that. And then we just add the offset and we have the function addresses. That's how we get the address of KEBugcheck and KEBugcheckX in this harness to submit to Nix to tell it that those are the panic handlers. If you want to see the implementation, it's all in this harness, so you can view the source code. And we submit those panic handlers. Okay, so at this point in time, we've done the basic agent handshaking, we've set the panic handlers, we've submitted our valid CR3. It seems I submit our CR3 twice by accident, but that doesn't actually matter. It's just overwriting it again with the same one, so that's fine. And at this point, we haven't snapshotted yet. We're just doing some general setup. Now we tell now we tell Nix the address of our payload buffer. We use this hypercall to tell Nix that this is the buffer we want Nix to put new test cases in as refuzz. And then we submit the IP ranges. Now what this is since it's using Intel processor trace to get and track code coverage, Nix needs a valid range of virtual addresses that it's going to trace with processor trace. By default, it's not going to trace just everything. You need to give it a start address and an end address, such that if I gave it the start address 0x13370000, and then I gave it an end address of 1339 followed by zeros, Nix is only going to track coverage where the instruction counter in the target is between these two ranges. So since I'm fuzzing a driver, I'm fuzzing my test KFL driver, I need the start address of this driver and I need the size. Because if I get the start address and the size, I can get the range. So in this case, if this is the valid range, I imagine that the size would be 0x20000. Because that means if I grab this start address and I plus this size to it, I'll get this end address range. So all I need is the start address and the size of our target. And that happens in set IP range. In set IP range, we call the enum device drivers Windows API, and we go through the Windows APIs to get details for loaded drivers. We query the name to see if it contains vuln driver, which is going to be part of the name of our driver. I compile my driver to vuln_driver.sys. So I go through all the drivers checking for this name. If I find a match, then buffer 0 contains the start address of that driver. Buffer 1 is the end of the range, so it's the start address of the driver plus the size of it. And then the, second index, or 0, 1, 2, 3rd, right, is set to 0 because I believe we can add multiple PT ranges. I think up to 2. We can add 2 ranges to trace. In this case, I'm saying that the first range is going to be this start here in buffer 0, and this end range here in buffer 1. And then I submit that as the range, or I submit the buffer as the range. So buffer 0 corresponds to the start of the range, buffer 1 corresponds to the end of the range, and buffer 2 corresponds to either the first, which is index 0, or the second, which is index 1, of the PT ranges that we can trace. I think we can trace up to 2 ranges with Nix. I haven't tested it, but from a look at the code, that's what it seems like. So we submit that range such that when we do a fuzzing, code coverage will be traced in our target driver. Once that's done, we get up to snapshotting. Now, when we call KFL next payload, this is going to cause a snapshot. KFL with Nix and QEMU is going to take a snapshot of the guest at this point, such that all the rest is fuzzing until it gets to KFL release. And then when it gets to KFL release, it's going to reset the snapshot back to the state of here when we did this KFL next payload command. Then it'll give us the next payload, go through our fuzzing, hit release, reset the snapshot back to payload again, and so on and so forth. And because it's a full device, full system fuzzer, it's resetting the state of everything, of the device, of memory, of CPU, of the entire guest. Now, at this point, we've hit here, we get to what happens when we're actually fuzzing. We call KFL acquire, and this requests a new payload. KFL will then inject into our payload buffer the new input, and then here, since I'm fuzzing the kernel, I pass the new input to the ioctl handler of the driver. In the payload buffer, we have a data and a size. These both get filled in by Nix. Nix will provide the raw bytes in the data offset to the buffer, and it'll provide the size of that data in this size entry of the buffer. So we do this to send our new input to the driver, and then the driver will eventually return code execution to us, and then we just hit this hypercall to reset. Now, between the snapshot and the resetting, if I wasn't fuzzing a driver, but I was fuzzing something else, I could just do anything I want here. I can fuzz a hypervisor by doing a custom hypercall or something. I could fuzz any other code by just interacting with it with our new input data and the input size. And then hit KFL release to jump back to the start of the snapshot. Simple, right? Cool. Now we understand how the harness is designed and how Nix roughly works. We can look into actually deploying this. Now this is powered by KAFL. KAFL, you can grab the necessary components from GitHub. On Intel Labs, if I just go to Intel Labs, there's a few things you'll have to clone. First, and that said, on my KFL targets GitHub, I have a rough README of what you need. First, you need to install the Nix kernel, right? So if I go to Intel Labs and I go to KFL, and you clone KFL, there's an install.sh. And install.sh has a few options. Let's see if I can see the options under usage. Here, these are the options. It can install dependencies, install QEMU, install KVM, perms, Redamza. Redamza is just a mutator, or all. I generally just run this with all, just to complete the installation. And I do believe that this will download the KFL kernel. Yeah, so this should pull down and build the KFL kernel. Let's see if I go down. Yeah, it tells you how to build and install it. You can just follow along this. If you're on Ubuntu or Debian, I tested this on Ubuntu. You can just run the included install.sh script. It'll build the components. It'll auto elevate to install and build the kernel. And here on step 3, where it says host KFL kernel, it tells you that KFL uses a modified KVM Nix kernel. It seems to have a pre-built release for Debian-based distributions, but on Ubuntu, I just ran this command after doing the building and installing for Nix, and you should be able to install using something like this, right? Where you install, well, first you clone it, you cd it to a directory of your choosing. You can create this work directory. You do make env. Also, you can use this clone command. Pretty much you can just follow the README as it is on here. You can do make install, do rest update host kernel, install the shkvm, this sudo dpkg command, and then reboot. And when you reboot, you may have to click advanced boot options to boot into um, your custom kernel that you just downloaded. Because sometimes when you do this installation process, it'll install multiple builds of Linux, of the Linux kernel, and only one of them will be the KFL one. You should see the KFL entry because it'll have KFL in the name. I'll show what that looks like a bit later, but you want to boot into that KFL kernel. So these steps on the README of Intel Labs KFL you can follow directly up until installing and jumping into the kernel. Now, I also cloned manually kfl.qemu and kfl.libxdc. Actually, no, wait, I don't think you need that, but I did build QEMU myself by grabbing kfl.qemu, which is also on Intel Labs, right? And you want to get the kfl underscore stable branch. That's the branch that has the customized QEMU, and it has the compiler for it. So now, once you've jumped into your custom KFL kernel, you can clone this kfl.qemu repo and check out the KFL stable branch. I'll open up my screen where I'm in a Ubuntu session that has that already. Let me just relaunch that. Okay. See if I can zoom in. Okay. So let me launch a new window instead. Just zoom in on this one. Okay, so I've got kfl.qemu. Now, in kfl.qemu, you do check out, I think it's -b for branch, and it'll be, was it kfl underscore stable? Right. If I go get branch right now, you see I'm in the kfl stable branch. And in here, you can do /compile qmunix.sh. Now, when you go to do that, it'll give you some options. There's different ways to build it. I've built it with just static. I think if you do LTO, you'll get a bit better performance at the cost of a larger compile time. But static builds pretty quickly, and it's worked pretty well for me as well. So you just do that to build it, and then that will build next to the current directory in x86 underscore 64.softmu slash qemu system x86 underscore 64. Now, now at that point, you have QEMU built. kfl.qemu is built. And now, before we get to fuzzing, we need to set up the target. I recommend having your target as a Hyper-V VM first or a VMware VM. Eventually, you'll convert it to a QCal2 QEMU format. But for setup, I find it's a lot easier to set up the target as a Hyper-V virtual machine or a VMware virtual machine first. So in here, I have my target. It's a Windows Server virtual machine. You want to install the driver. So in here, I've got, what did I call it? Next test. On your machine, you should call it vuln underscore driver.sys to work with the harness. Let me just copy that. So you should have the driver compiled, right? And to compile the driver.c file, you can create a driver WDM project in Visual Studio Community or Enterprise or whatever, and just compile it as a driver. And you'll get a vuln driver.sys. And with this vuln driver.sys, you want to plant that on your target. And here I've planted it in C drive temp. Since I compiled this without a valid certificate, you'll have to do bcd edit /set test signing on, and then you'll have to reboot your machine. In this case, I already have that enabled, so I don't have to reboot. And I want to tell this driver to start on boot, because when KFL goes to run my target before snapshotting, it doesn't actually give a GUI. So I'm not going to be able to interact with my target in such a way to manually run the driver. Now, there may be a way to, easily do something like that or get comms into there. I haven't bothered looking at that at this point. Instead, I just tell everything to run on boot, such that when the fuzzer runs my QEMU target, it will automatically execute my harness code and snapshot. So first thing, get the driver running on boot. To do that, we can use sc create. I'm going to call it vuln_driver. You can call it whatever you want. Bin path equals to space the path to the driver. Type equals to space kernel. And here start equals to space auto. This will tell it to auto start this driver on boot as a kernel driver. Now, I'm not going to run that because I already have an entry. Next up, you're going to have your harness, which I have as vulntest.exe. This is the harness code we've been looking at. Now we want this harness code to auto start as well, because that's going to be what actually does the snapshotting. But you want to auto start it after the driver has been loaded. Otherwise, if vulntest goes to get a handle to the driver, but the driver isn't loaded yet, there'll be problems. So you can do the same sc create command with sc create, I'm going to call this harness, bin path equals to c drive temp vuln_test.exe, type equals to, actually you don't need type. Instead here you can just do start equals to space delayed -auto. This means it'll auto start, but it'll auto start after everything else that auto starts has finished starting. So this means by running those two commands, the next time I boot this machine, the driver is going to automatically start, and then my harness will automatically start with no user interaction. Now, like I said, there probably is ways to maybe remote into the guest with VNC, or do something like that to get it running. I think if you compile QEMU using the KFL built compiler, so if I look at KFL, in install.sh, so let me go back to the KFL directory. In KFL, there was this install.sh, and in here there was an option to build QEMU right here. You'll download and build modified QEMU. Now this, when it builds it with VNC, such that when you run your guest, you can remote in with VNC. You might be able to modify the build script that we saw in kfl.qemu to include VNC support and launch it with VNC. Or presumably, you might be able to set your QEMU_path, QEMU_root, because when you build QEMU using this script, install.sh, it finds QEMU at your environment variable called QEMU_root, and then it builds it. So presumably, you can either have this build your kfl.qemu, or, which I haven't tested by the way, but I know that when you build it this way, it does use VNC when you run your guest. But presumably you could just use VNC when you run QEMU, or compile it with your kfl.qemu. The point is, with VNC, you might be able to VNC into the target and manually do stuff to trigger the snapshot. instead of having things start at root. Presumably I could set this QEMU root environment variable using something like export QEMU underscore root equals to um, slash home, my user, source, kfr.qemu, and then do install.fhqemu. And then it might install QEMU with VNC, and then I can just connect to QEMU using VNC, which is a documented method of connecting to QEMU. And then I wouldn't have to auto start things. I could just, before the snapshot is taken, VNC into my guest and log in and manually run my harness, at which point the guest will snapshot, and then I can just exit VNC and it'll fuzz. Like, presumably that will work. I haven't done that. I've only done it this way where where I build it using the install script in kfl.qemu instead of this one here in the base kfl repo. Um, and I have it auto start, but this could work as well. So this you might want to explore if you're fuzzing something where you may need to manually log into your guest and like trigger something. So at this point, we have our QEMU. We have our guest set up to auto start. In this case, I can shut down the guest, and you want to convert the guest into a QEMU image. So to do that, you just do QEMU dash image. Right, you should have that on disk somewhere. I've got that on D drive. QEMU just image. You can do dash capital O qcal2 to tell it we want to convert the file to a qcal. Path, and you pass it the path to your VM file. Mine is in D drive, Hyper-V, vdisks, server standard.bhd. And then I want to output to that to D drive temp windows.qcal2. I hit enter and they'll convert it. Now, when you're converting this, you want to make sure that you don't have any snapshots. So you can see on the settings for my Hyper-V VM, I've got checkpoints disabled. I think for VMware, you want to make sure that there's no snapshots and things like that. And there's no split disks. It's just the one VHD or the one VMDK. There should be documentation even on Google for just converting VMware images and Hyper-V images to QCal2s. Should be pretty straightforward. Once this is done, you'll have your QCal2 file. You'll copy that to your Nix host, which I have here. And now at this point, you want to create an overlay image. So if I go to disks, I've got windows.qcal2. Now you'll start with just that, and then you want to create an overlay. The overlay is what you use for fuzzing. So here you could do qemu-image, create -f qcal2, and then -b for it to be an overlay or something like that, /windows.qcal2, and then the output name, which is going to be overlay underscore 0.qcal2. Now with this command, it'll generate the overlay file, and the overlay file is what we're going to use to actually fuzz red. Now, with that running, make sure when you're in your work directory here, you've done make env, and that'll, let me exit. So I cd'd to this directory and did make env, and did all that stuff. This is where my KFL lives. Now I can cd to KFL, and I can run the fuzz command. I've saved an example one in fuzz underscore kfl.text. I'm just gonna type it out because it's not 100% accurate either, but it's Python 3 kfl underscore fuzz.py -w. This is going to be where your outputs are going to live. The fuzzer is going to manage a whole bunch of fuzzer stats and state in this folder. I'm going to put that in output underscore fuzz. --image is going to be path to the overlay. I have it in disks overlay. -m is how much RAM it's going to run the target gas breath. I'm going to use 3 gigs of RAM. I'm also passing the path to Redamza as an additional input vector. I have Redamza in this location here, in this bin, in Redamza, bin Redamza. I think I got Redamza just straight from GitHub. I think I did GitHub, Redamza, And oh, I wonder if it was one of them, or I wonder if KFL had Redamza in it. I mean, Intel Labs. Nope. Let me go to Redamza and do git branch, git remote-v. Ah, I got Redamza from gitlab.com/akihe/redamza.git. I'm not sure if you actually need Redamza. It's just another mutator, and I've included it. So I just pass the path to it there. Then you pass the path to QEMU, and to me that is in my home directory, my user, source, kfl.qemu, x86, softfmu, and then the actual binary right there. And then I do dash dash purge just to dash dash purge means if there's anything in that output directory already that you pass with dash w, it'll delete everything in there. I also do dash dash overlay equals to double quotes. This is because I think by default, without specifying this, it tries to call QEMU with a overlay prompt, well, with an overlay value. But because we're using a QCal2 to fuzz with and not like a Linux image on disk, the overlay command is actually invalid. So I just do this dash dash overlay space double quotes to make sure that we're not passing anything for the overlay command. There's other options as well. You know, if I just do Python 3 kfl underscore fuzz.py dash h, I can spell Python correctly, you'll see a whole bunch of options. And even when fuzzing, there's also red creen and Grimoire that you can specify. Red creen is helps with input generation and mutation. There's a full paper on it that you can read about. Grimoire, it says analysis and mutation stages. I'm not entirely sure what this is, but it's something you can look into as well. So it would be worth looking into those options to enhance your fuzzing. But that command line that I had before, let's scroll up. This command line, let me just zoom out a little bit. Yeah, this full command line here, presumably, well, not presumably, but when you hit that, what's going to happen is you'll see something like this, where it launches the KFL fuzzer. No PT trace region is defined. This is because you can hard code the PT trace regions, those start ranges, in the command line. In our case, I'm not doing it via command line, I'm doing it dynamically in our harness. It shows what commands it uses to run QEMU, and then it'll boot the QEMU. Now, at some point, it will reach this point where you'll see that the harness submitted the bug check handlers and it printed out the host config stuff, and then it snapshots, and you'll see worker 00 is ready. And now you just see it fuzzing. I can see it's getting around 2,000 executions a second, 2,394 executions a second, and in KFL, there's a KFL underscore gui.py, and you provide that the path to the output folder, which I specified as output fuzz, and it gives you a nice input. My terminal's too small. Let me reset my terminal size and run that. Okay, now you see a nice GUI here. You can see the current executions a second is 2,500. You can see the stability is 99%. Workers is 1 out of 10. This is because I have 10 threads, or actually, I think I have 10 cores. Yeah, I've got 10 cores on this machine, and it's only using one of those cores. I think there's a -p command. If I go Python 3 kfl underscore fuzz.py -h. I need to make env first, and then in make env, do that, run that script. Now let's see. -p, the number of parallel processes. Yep, so you can provide a high value for dash P to use more cores instead of just one core. But even with just one core, I'm hitting 2,500 executions a second. Not bad. But remember, the more cores you use, the more your memory is going to be used as well. You can see I've already found one crash, and I found 12 inputs that stress new coverage. You can see that because the total paths is 12, that it's found new paths, which means code coverage is working. It's found new coverage. And yeah, that's the main part of that. If I look into the output, there's different folders. One of them is is it corpus? Yes, under corpus, you have crash. And in crash, you have the input that caused the crash. So if I dump that, you see that the input is a bunch of things, but it also contains Pwn Town, right? And we saw that that's the text needed to cause the crash in the driver. And it found this on its own. So that's cool. So at this point, it's fuzzing. And that's a simple example of fuzzing a kernel driver using Nix. Um, Before I show the booting into it, using the showing off the different kernel entries, let me just make sure I haven't missed anything. .com slash Paras12 slash targets. And to build the targets, by the way, you can just run the compile.sh script included in the Windows x86-64 directory from my updated branch that includes the Nix changes. If you want to see exactly what changed, you can compare. I think history might tell you. Yeah. So you see update vuln underscore test.c for Nix fuzz mode. You'll see all the changes I added to support Nix fuzzing in the harness. If I go back just to the base of it, okay, rebuilt QEMU, you can either use that or you can use similar. The example target, I have an example here in the command line. Oh, actually, the command line was missing one thing. My bad. So with the command line, right, you also want a dash dash seed dash dir and then a path to an inputs folder. Now your seeds are going to be your starting inputs. So I can do like echo, I don't know, my first input and put that into input one, right? Seed dir is going to be the path to where you store your initial corpus. So what I'm going to do is I'm going to update this very quickly. So actually, let me go here. Here. Okay, dash dash purge. It's also going to be dash dash seed dash dir equals to let's do inputs and dash dash overlay. No, not overlay. Dash dash append double quotes. Okay. So when we look at what I actually ran, if I scroll up here, you'll see I ran it with a seed directory pointing to my initial inputs, as well as dash dash append that. Now I don't think you actually need a seed directory, but it's good to have a starting set of inputs, or valid inputs for your target, whatever your target is. I just quickly updated that command line on the repo. So on the repo, it shows dash dash append that. Since I have that, I don't actually need that one anymore. So let me just quickly do that. Cool. So now the command line is on my Git. It shows the dash dash append and dash dash seed as well. So that should be fine. And you get a fuzzing? Yep. Okay, now let me cancel this fuzzing. And let me reboot to show you what it may look like when you first install the Nix kernel and how you can boot into that custom kernel. Let me just make sure it boots from the hard disk drive. Okay, so on this boot screen, for me, when I installed the KFL kernel, I needed to go to advanced options for Ubuntu. And then down here, I see the KFL kernel. It's got KFL in the name. And then I just hit enter on that to boot into KFL. Pretty simple. But that's what I needed to do in order to boot into that kernel. And then from there you can build, you can do the fuzzing as we were doing.